Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. The curious case of white dwarfs. The stellar furnace. Imagine a colossal ball of hot gas, millions of times larger than our sun, swirling in the vast emptiness of space. This is a star in its prime, a nuclear furnace powered by a delicate dance called hydrogen fusion. At its core, under unimaginable pressure and temperature, hydrogen atoms are constantly colliding, merging into helium atoms in a process that releases tremendous energy. This energy radiates outward, bathing the star in a brilliant glow and warming the planets that orbit around it. Our Sun is a prime example, a star halfway through its main sequence life, radiating warmth and light that sustains life on Earth. But this magnificent display of stellar power isn't a limitless wellspring. Just like any fuel source, the vast reserves of hydrogen within a star are finite. Over vast stretches of time, measured in billions of years, the core slowly but surely depletes its hydrogen supply. The inevitable shift. As the core's hydrogen fuel dwindles, the delicate balance within the star starts to tip. Fusion slows down, and the immense outward pressure generated by the fusion process weakens. Without this counterforce, gravity takes over. The core begins to contract, its immense density rising as it shrinks under its own weight. This contraction, however, has a surprising consequence. As the core gets denser, the remaining hydrogen becomes even more tightly packed, actually increasing the fusion rate for a short period. This temporary boost in fusion pushes the outer layers of the star outward, a bit like squeezing a balloon. The star swells, its surface area growing significantly. It becomes a red giant, a majestic titan bathing its surroundings in a cool, reddish glow. The red giant's farewell. The red giant phase is a dramatic turning point in a star's life cycle. While the core undergoes a period of intensified but unstable fusion, the outer layers, no longer held tightly by the core's pressure, begin to drift away. This stellar shedding forms a magnificent planetary nebula, a vast, colorful cosmic cloud composed of gas and dust expelled by the red giant. The expelled material enriches the interstellar medium, providing the raw ingredients for future generations of stars and planetary systems. It's a bittersweet farewell, a dazzling display of stellar generosity that marks the end of the star's main sequence life and the beginning of its transformation into a white dwarf. The cinder of a star, the birth of a white dwarf. The expulsion of the outer layers in the red giant phase leaves behind a dramatic remnant, the star's core, exposed and naked. This core, once the bustling heart of a star, is now a compact, incredibly hot object called a white dwarf. Imagine squeezing the mass of our Sun down to the size of Earth. That's the incredible density of a white dwarf. The intense gravity during the red giant phase has crushed the atoms within the core, forcing electrons to occupy the lowest possible energy levels. This might seem stable, but it's a precarious situation. Normally, electrons was around the nucleus in distinct shells or orbitals. But in a white dwarf, these electrons are crammed together, defying the usual rules of atomic structure. The dance of degenerate matter. The unusual state of matter within a white dwarf is called electron-degenerate matter. It's a special kind of pressure that arises from the degeneracy pressure exerted by the jammed electrons. Imagine a crowd of people crammed into a room. If one person tries to push in, everyone else pushes back with equal force. This is analogous to what happens in a white dwarf. The electrons, crammed together, resist any further compression. This degeneracy pressure acts as a powerful counterbalance to the immense gravity of the white dwarf, preventing it from collapsing further. It's a cosmic tug-of-war, with the electrons holding their ground against the immense gravitational pull. This electron degeneracy pressure is a fascinating phenomenon in physics. It's a state of matter that only exists under the extreme conditions found in white dwarfs and neutron stars. It's a testament to the strange and wonderful properties of matter under extreme pressure. A ghostly glow and the long goodbye. The white dwarf, born from the ashes of a red giant, is a faint ember compared to its former stellar glory. The immense heat generated by the core during its main sequence life is slowly radiated away. The white dwarf emits a faint, white light, a ghostly echo of its past brilliance. This light comes from the remaining thermal energy within the core and the slow release of gravitational energy as the white dwarf slowly shrinks. The fate of a white dwarf is one of slow, gradual cooling. Over billions of years, it will radiate away its heat, becoming a dark, cold object known as a black dwarf. However, for most white dwarfs, this is a very distant future. They are fascinating remnants of stellar evolution, offering astronomers a window into the life cycle of stars and the ultimate fate of our Sun. Beyond the pale glow, unveiling the secrets of white dwarfs. While white dwarfs are faint compared to stars actively undergoing fusion, astronomers have developed clever techniques to study them. By analyzing their faint light, we can determine their temperature and composition. Additionally, the Doppler effect, a shift in wavelength caused by motion, allows us to measure the white dwarf's velocity and sometimes even detect the presence of a companion star. These observations have revealed a surprising diversity among white dwarfs. Some are composed primarily of helium, the byproduct of hydrogen fusion. Others are dominated by carbon and oxygen, hinting at more complex fusion processes that might have occurred in their earlier stellar lives. By studying the variety of white dwarfs, we can piece together a more complete picture of stellar evolution and the different pathways stars can take. The dramatic duo: white dwarfs in binary systems. The story of white dwarfs doesn't end with their solitary cooling. Many white dwarfs exist in binary star systems, where two stars are gravitationally bound. In these systems, a fascinating phenomenon can occur. If the white dwarf has a companion star that is still undergoing fusion, the white dwarf can siphon off gas from its neighbor. This stolen fuel can ignite in a runaway fusion reaction on the white dwarf's surface, causing a spectacular brightening called a nova. Imagine a dying ember suddenly flaring back to life. Novae can be incredibly luminous, briefly outshining the companion star. But the drama doesn't stop there. In some cases, repeated episodes of gas accretion from the companion can lead to a thermonuclear explosion even more violent than a nova, a type Ia supernova. These brilliant explosions are crucial for astronomers, as they are considered standard candles because their peak brightness is predictable. By measuring the apparent brightness of a type Ia supernova in a distant galaxy, astronomers can determine its distance, a vital tool for mapping the universe. A diamond in the rough: the curious case of crystallization. Recent discoveries have challenged our understanding of white dwarfs even further. Theoretical models suggest that under specific conditions, the immense pressure within a white dwarf can cause the carbon and oxygen nuclei to fuse, forming a crystalline lattice structure. In essence, the white dwarf's core could transform into a giant diamond. While this might sound like science fiction, astronomers are actively searching for evidence of crystallized white dwarfs. By analyzing the way light interacts with the white dwarf's atmosphere, they hope to detect subtle signatures that would reveal the presence of a crystalline structure. The possibility of giant space diamonds is not just a scientific curiosity. It sheds light on the complex processes occurring within white dwarfs and provides valuable insights into the behavior of matter under extreme pressure. A legacy written in starlight: the enduring significance of white dwarfs. White dwarfs, these faint stellar remnants, are more than just the cinders of dead stars. They are cosmic archives, holding vital clues to the life cycle of stars and the ultimate fate of our Sun. By studying their properties, we can understand the delicate balance of forces that govern stellar evolution. They are a testament to the power of nuclear fusion, the dance between gravity and pressure, and the strange properties of matter under extreme conditions. The faint glow of a white dwarf might seem insignificant compared to the brilliance of a star, but it represents a crucial chapter in the grand story of the universe, a story that is far from over. As we continue to unravel the secrets of white dwarfs, we gain a deeper appreciation for the intricate dance of life, death, and rebirth that plays out across the vast cosmic stage.